Our group tackled the problem of accurate online localization of a highly dynamic aerial vehicle using stereo vision odometry and inertial measurements. This is analogous to a GPS-denied low-cost aerial vehicle. We use GTSAM, which is a library that supports nonlinear factor graph optimization. Factor graphs are graphical models that we use for our SLAM estimation problem. This is a visualization of the factor graph we use for SLAM, where the x 0 to 3 white nodes represent robot poses in each camera frame. The I 0 to 2 nodes represent landmarks taken from stereo vision odometry, SVO, from the camera images. The green nodes represent transforms calculated between frames using detected features in RANSAC. The black nodes represent IMU factors between frames. There are multiple IMU factors that must be combined in some way. And the blue nodes represent factors derived from landmark locations. This is dataset 1, which consists of a simple loop by a handheld quadcopter. We found visual features using the onboard stereo vision and inertial measurements, using the onboard IMU. Using both, we localized the aerial vehicle using factor graph and GPS-denied locations with cheap sensors. In this dataset, there is ground truth Vicon data and the environment is feature-rich. This is dataset 2, which consists of blank hallways, large loop closures, and a self-flying quadcopter. We set ourselves the task of having an average error of less than 1/5 from the ground truth dataset, run as close to real time as possible, maximizing at 10 minutes, solve semi-sparse regions like blank hallways, and closing large loops. We don't have the ground truth for this dataset. This is Nathan Michael's results from dataset 2. We know the map should look kind of like this, but we don't have ground truth. The IMU data comes in at a higher rate than the images do, and so the data must be simplified in order to work as IMU factors. The top images show how the IMU updates compare with the camera updates and illustrate the need for a simplified graph. In order to pre-integrate the IMU, we gather all of the updates between subsequent camera updates and integrate the data to find a change in position, velocity, and orientation between the camera updates shown in the top image. These simplified values are put into the factor graph. For the visual odometry, we are using SIR features. These features are compared between each pair of images and matched. These matched features are triangulated using the camera matrix. Features are matched between every frame as well. These frame-to-frame matches in 3D are filtered using RANSAC, and a transformation matrix between each frame is calculated. We keep a list of these features and use some of them as landmarks within the factor graph. Our results show a fairly accurate trajectory for the quadcopter in dataset 1. There's an approximately 20-degree rotation offset in the XY plane to the Vicon's systems coordinate frame being off by 20 degrees compared to our visual odometry frame on the quadcopter. The landmarks of the factor graph can be seen as the green coordinates in the video. For dataset 1, we use the stereo visual odometry as the initial and the features with IMU as the factors in the graph. This worked well, but had to be tuned carefully. When moving to dataset 2, there are large featureless regions in the backside of the hallways. When using the stereo visual odometry as the prior, there is no way to get viable output. We believe we would have had better results with IMU as the initial, but our algorithm was tuned carefully with the stereo visual odometry as the initial. In order to get this to work on a quadcopter, all functionality, including stereo visual odometry, IMU pre-integration, and a factor graph localization, would need to be converted fully to a more rapid environment, which includes a C++ implementation and an online ISAM approach rather than the batch approach used here. Better feature tracking could also be incorporated to allow for better loop closure. Thank you to Michael Case, Chris Gattani, and our TAs for this class. Thanks also goes to Nathan Michael for the datasets used in our experiments.